Here we're going to look at an interesting problem that came from the American Mathematical Monthly. So it's kind of a combinatorics problem in that we're counting some things, but we're also going to use some linear algebra along the way. So what we want to do is decide how many ways a 2n by 3 rectangle can be tiled by 2 by 1 tiles. So maybe the first thing to do is to play some games with the very starting cases of this, like n equals 1 and then n equals 2, and see if we can use that to like generalize an idea for some arbitrary n. So let's maybe go ahead and look at the n equals 1 case first. So notice for the n equals 1 case, that means we're talking about a 2 by 3 rectangle. So let's maybe go ahead and get a 2 by 3 rectangle drawn on the board. Okay, there, we've got 3 different 2 by 3 rectangles on the board, and that's maybe a spoiler alert because there will be 3 ways to tile this with a 2 by 1 tile. So what I mean by a 2 by 1 tile is maybe something of this form. So it looks like that, and then I'll maybe shade it in orange to have the shading be the tiling. Okay, so now just to make it clear which tiles we're using, I'll use an orange tile, a purple tile, and a green tile. So the first way to tile this would be with 3 horizontal tiles. So maybe I'd shade it in like that, and then like that. So there I've got my orange tile, my green tile, and then my purple tile. So that would be maybe the easiest way to do it. And then next we could shade in the orange tile horizontally like this, and then the purple tile vertically, and then the green tile also vertically. But now if we look at this second method, there's actually a symmetric version of this second method. So pay no mind to the color because we want to think about the color as just being distinguishing so that we can easily reference the picture. But we could put our horizontal tile at the bottom. That's our other choice here. So let's maybe go ahead and do that. We've got our orange horizontal tile at the bottom. And then we've got our purple tile, which is vertical. And then our green tile, which is also vertical. So it looks like for n equals 1, we have 3 different possibilities. So let's maybe use the notation that a sub n is this number right here, the number of ways a 2n by 3 tile can be tiled by 2n by 1 tiles. So here we'll say that a sub 1 is equal to 3. So there are clearly 3 methods. Now let's look at the next case, the n equals 2 case. So notice that's going to be a 4 by 3 tile. Next, I'll notice that in this n equals 2 case, we can either start with 2 tiles that are of this form, which gives us 9 possibilities because that's 3 squared, plus what I'll call new tilings. And those are tilings that are not built by 2 of these choices from our 2 by 3 tiling. So let's get some pictures of 4 by 3 grids on the board, and then we can count up the new tilings. Okay, so now we've got 2 copies of our 4 by 3 tiling on the board, and that's actually all the new ones that we'll need. So let's see how we can tile this in a way that doesn't use a starting point from our n equals 1 case. So first off, we could maybe put a vertical tile here, which I'll draw in red, and then 2 horizontal tiles here, and then like that. And then next we could have another vertical tile over here, and then finally 2 horizontal tiles underneath. So notice that gives us a new tiling for this 4 by 3 rectangle that's not possible by building it out of these pieces of 2 by 3 rectangles. Okay, but now if we look at this, we'll see that there's a symmetric version of this that we get if we just flip it this way. So let's draw that in. We could have 2 horizontal pieces on the top, so like that, and then like that. And then next we could have our vertical pieces on the edges. So that would be like here, and then also like here, and then 2 horizontal pieces in the middle. So maybe we could have one of those be blue and one of those be green. So that gives us 2 more possibilities. So let's see. That means that we can count up our a sub 2, and our a sub 2 will equal 9 from building it out of 2 choices of these, plus 2, or a sub 2 is equal to 11. So we've got our first 2 cases taken care of. Now let's clean up the board and we'll talk about the general case a little bit. So far we determined that there were 3 different ways of tiling the n equals 1 case, 11 different ways of tiling the n equals 2 case. Now we're ready to look at the general n case. So let's draw a couple pictures to motivate our argument. So I'll start off with a rectangle like this. So this is going to have a height of 3, and then it'll have a width of 2n. Notice that I can cut off a 2 by 3 piece on the side, and we know exactly how many ways that we can tile this 2 by 3 piece, and that is 3, because that's equal to a sub 1. And then we also know exactly how many ways we can tile this thing, which I'm kind of shading in pink. And that's because this has width 2n minus 2, or 2 times n minus 1. So we know that we can tile this a sub n minus 1 different ways. Now we're going to play the same game, but we'll cut off a 4 by 3 piece from the start. So I'm going to have my same rectangle. So this is going to be 2n on this side. It'll be 3 on this side. I'm going to cut off a bigger piece. This piece is going to be 4 units on this side. That makes it 2 times n minus 2 units on this side. But now we know how many new ways we can tile a 4 by 3 rectangle. And by new, I mean the ones that are not covered up in this case. There are 2 new ways of tiling this bit. And then we also inductively know how many ways to tile this 2 times the quantity n minus 2 rectangle, and that's a sub n minus 2. Oh, so that's nice. But we can put this together to form a recursion for a sub n. So notice a sub n will be the total number of ways to tile a 2n by 3 rectangle. Well, we get 3 ways for each a sub n minus 1. And then we have 2 new ways attached to this 2 times n minus 2 by 3 rectangle. So we can write that as plus 2 times a sub n minus 2. So now we'll need to solve that recursion to find a closed form for a sub n, and that's exactly what we'll start doing on the next board. So far we determined that if a sub n was the number of ways we could tile a 2n by 3 rectangle with 2 by 1 tiles, then that number a sub n satisfied a certain 2-step recursion. So a sub 1 was 3, a sub 2 was 11, and then a sub n was equal to 3 a sub n minus 1 plus 2 a sub n minus 2. Now we want to solve that recursion to get a closed formula, and we're going to do that using linear algebra. So there's several ways to solve a recursion to get a closed formula. In this video we use linear algebra, although we used other methods in the past. So I want to recall the diagonalization procedure for a 2 by 2 matrix. So if A is a 2 by 2 matrix and it has eigenvectors and eigenvalues v1 lambda 1, so v1 is the vector, lambda 1 is the value, and then v2 lambda 2, then if we set P equal to the matrix formed by the eigenvectors, so the first column is v1, the second column is v2, then P inverse AP is this diagonal matrix with the entries, the eigenvalues. So we have lambda 1, lambda 2, and then the rest zeros. So this is actually going to be pretty helpful because what we can notice is that this recursion gives us the following like matrix relationship. So we have a sub n minus 1 as a vector is actually equal to the matrix 3, 2, 1, 0 times the vector a sub n minus 1, a sub n minus 2, like that. So by the standard rules of matrix vector arithmetic, we can see that this vector equation is the same thing as this recursion on our a sub n's. So next what we want to do is diagonalize this matrix 3, 2, 1, 0. So let's maybe give this thing a name. So let's set A equal to 3, 2, 1, 0. And in order to diagonalize it, we need to find the eigenvectors and the eigenvalue. So let's first find the eigenvalues. So we do that by looking at something called the characteristic polynomial, which I will denote by P sub ax. And that's equal to the determinant of x times I minus a. Good. So that ends up being the determinant of the matrix x minus 3 minus 2 minus 1x. So that's what we get if we do this combination here, xi minus a. And here I've used these like straight lines on either side to mean the determinant. So let's see what we get for that. Multiplying this out, we get x squared minus 3x minus 2. So if you recall, the eigenvalues are the zeros or the roots of the characteristic polynomial, which means we need to solve this equation x squared minus 3x minus 2 equals 0. And we can do that with the quadratic formula. So we'll notice that we get x equals 3 plus minus the square root of 17 over 2. So again, that's just with the quadratic formula. So that tells us what our two eigenvalues are. So I'll call them lambda 1 and lambda 2. So we have lambda 1 is 3 plus root 17 over 2. And then we'll call lambda 2 3 minus root 17 over 2. So let's maybe put some boxes around these. Now, in order to find the eigenvector associated to this eigenvalue lambda 1, we need to look at the null space of this matrix lambda 1 times the identity minus a. So again, that's how you calculate the associated eigenvector for a given eigenvalue. So let's see what that gives us. So that's the null space of, well, plugging in lambda 1 into this object right here will give us minus 3 plus root 17 over 2, minus 2 minus 1, and then 3 plus root 17 over 2, like that. So now we want to start row reducing that, and we'll row reduce it until we have a clear idea what the null space is. So maybe I'll first swap the bottom row with the top row just to get a 1 kind of in the nice pivot position up there. I'll also negate this bottom row while we're at it. So this is going to give me the null space of 1, and then we have minus 3 minus root 17 over 2, and then minus 3 plus root 17 over 2 minus 2. Great. So that's just by swapping rows. So next, I want to zero out this element right here. So I'll maybe like circle that in yellow, and I can do that by multiplying the top row by the opposite of that. In other words, what I want to do is take 3 minus root 17 over 2 times row 1, add it to row 2, and have that become my new row 2. So let's see, why that multiple of row 1? Because this is equal and opposite to this thing that I have circled in yellow, which means it'll cancel that term out. So let's see what that gives us. That gives me the null space of, so I have 1 minus 3 minus root 17 all over 2. So my first row did not change. And then this becomes 0 by design. Next, notice multiplying this 3 minus root 17 over 2 with this minus 3 minus root 17 over 2 will give us exactly 2. And that's not too hard to see just by carefully multiplying it out, but that means that gets canceled with this thing right here. So we also have this as a 0. But now that we have this thing totally row reduced, let's clean up these last few calculations and then we'll calculate the eigenvector. So via row reduction, we determined that the null space of lambda 1 I minus a is the same thing as the null space of this simpler matrix. Remember, the null space of lambda 1 I minus a is the same thing as the lambda 1 eigenspace. So that means that if we have a vector, which I'll give entries a, b inside of this null space, then it's also an eigenvector with this eigenvalue. So I'll call this v1 here. But being inside this null space means that we are obliterated or annihilated by this matrix. In other words, we know that this matrix 1, 0, minus 3 minus root 17 over 2, 0 times AB must give us the 0 vector 0, 0. That's the definition of being in the null space. But now by matrix vector multiplication, we can see that that tells us that A minus 3 plus root 17 over 2B 0 is equal to the 0 vector. But next, that tells us that A has to be equal to 3 plus root 17 over 2 times B, where B is a free variable, but that's okay because any multiple of an eigenvector is also an eigenvector. So since we want maybe the simplest eigenvector, let's maybe go ahead and set B equal to 1. And that tells us that our V1, in other words, the appropriate eigenvector that we can use, is of the form 3 plus root 17 over 2, 1. So those are the entries there. So we figured out this first eigenvalue. So I'll maybe put a check there. And then through a similar method, we can figure out an eigenvector for lambda 2 as well, but I'll let you guys do that. And we'll just jump to the next board with those facts. On the last board, we determined the eigenvectors and eigenvalues of the matrix. So we calculated one by hand, and then you can calculate the other one pretty similarly. So we've got this eigenvalue lambda 1 with vector v1, and eigenvalue lambda 2 with vector v2. Now we're ready to use this diagonalization procedure to simplify our matrix A. So if we set P1 equal to the matrix formed by these eigenvectors, so I'll write it out. This is going to be 3 plus root 17 over 2, 1, and then 3 minus root 17 over 2, 1. Then we have P inverse AP is equal to, well, it's this diagonal matrix with the eigenvalues on the diagonal. So we have 3 plus root 17 over 2, 0, 0, 3 minus root 17 over 2, like that. Okay, but what we really want is a simpler version of A. So we can do that by moving around the P inverse and the P, and that's going to give us A equals P times our diagonal matrix. So that's going to be 3 plus root 17 over 2, 0, 0, 3 minus root 17 over 2 P inverse. And then also with pretty standard methods, we can find the inverse of P. So let's maybe write the inverse of P down here. And then we'll jump to the next board where we have inserted A with P times the diagonal matrix times P inverse all in one piece. So the inverse actually has the form 1 over root 17 here, minus 1 over root 17 here. And then next we have minus 3 plus root 17 over 2 times root 17. And then next we have 3 plus root 17 over 2 root 17. Great. So again, let's jump to the next board where we have some of this laid out. So we just did a lot of work to translate our recursion with our two seeds A1 is 3 and A2 is 11 into a nice matrix vector equation. So I won't read it off because it's like quite complicated. Now what we'll do is repeatedly apply the product of these three matrices to maybe like a starting vector to achieve this vector right here. And that's like a standard trick with these recursions, is that you can repeatedly apply the recursion by raising the matrix to the certain power. So let's start all the way at the bottom here. And I want to start here with 3, 0. So that would be like A1, A0. So notice if I'm starting at A1 and I'm ending at AN, that means I need to apply this operation n minus 1 times. But since this matrix and this matrix are inverse pairs of each other, that power of n minus 1 only builds up in this middle term right here. So we get an n minus 1 up here. But with that structure, we're actually ready to find our closed form for our a sub n. And we're going to do that by introducing some new notation just to make it a little bit easier to write down. So I'm going to set alpha equal to 3 plus root 17 over 2 and beta equal to 3 minus root 17 over 2. Notice those two numbers show up all over the place in our matrices, so that's like a standard trick to do to make it look a little bit simpler. So that gives us our matrix vector equation will be an minus 1 is equal to alpha, beta, 1, 1 there. And then we'll have alpha to the n minus 1, 0, 0, beta to the n minus 1. Because taking n minus first power of a diagonal matrix is pretty simple. You just do that. Okay. And then next we'll have, well, let's see what we can do. We can factor out a minus 1 over root 17 and then have this in terms of alpha and beta as well. So I'll just jump to the end of that. We'll have minus 1 here, 1 here. We'll have beta right here. So that's what we get from factoring a minus 1 over root 17 here. And then we'll have minus alpha here, again for the same reason. And I'll go ahead and take that minus 1 over root 17 and I'll put it here as minus 3 over root 17. Then another thing to do is maybe we shouldn't have taken a minus sign out. So let's take this minus sign and put it back into this matrix. So that'll just change all of the signs. And now we've got something that looks a little bit nicer. Now we're ready to do our matrix vector arithmetic, and we'll end up with our closed form for a sub n. So let's multiply these two matrices, and then we'll multiply the last matrix with the vector. That'll give us alpha n, beta n here, and then down in the bottom entry, we'll have alpha n minus 1, beta n minus 1. Good. Then via matrix vector arithmetic, we will have 3 over root 17 in that entry, and we'll have minus 3 over root 17 in the bottom entry. Now we're ready to finish it off. So by this final matrix vector arithmetic, we'll see that our top entry will be given by 3 over root 17, and then alpha to the n minus beta to the n. And the lower entry will be essentially the same thing, but with n minus 1 exponents. So we'll have 3 over root 17, alpha to the n minus 1, minus beta to the n minus 1. But reading off the appropriate entry from this matrix, we see that a sub n will be equal to this object right here. Now, resubstituting our alpha and beta, we see that a sub n is 3 over square root of 17. And then we'll have 3 plus root 17 over 2 all to the nth power minus 3 minus root 17 over 2 all to the nth power. And that's our nice closed form for this tiling problem. And that's a good place to stop.